This is part 2 of lecture 24, in which we'll talk about the theoretical background for response surface methods. Now, I asked a couple of weeks ago for you to start to think about experimental design in a slightly different way. The kinds of questions that we set about to try to answer was whether or not there was relationship between independent variables and a desired response variable, and experimental design was a collection of tools and techniques to go about trying to answer such questions in a rigorous or objective manner. But you can also use the principles of experimental design to answer a different kind of question, and that's a question of optimization, or finding the best or finding the worst operating conditions, or what are the values of the factors for which I'll get optimal output. If you think about some of the kinds of examples that we've talked about, especially those that are associated with manufacturing or production plants, what is the optimal value of a temperature or a pressure or the kind of material to give you the maximum yield. And the underlying assertion in response surface methods is that the best way to go about answering those kinds of questions is through rigorous experimental design, and not just haphazardly trying different operating conditions, or in our language, and not just trying haphazard level values for the factors, but to go about using these rigorous principles that we've been studying for the semester. So response surface methods are not just statistical methods, but there's an associated set of mathematical methods, those of optimization, for which modeling, which we've done, and analyzing problems, which we've also done or doing, and where there's a response variable of interest, but we're not just looking to explain the variation or to determine if there is a relationship between variation in factors and the response variable, but the aim is to optimize the response, to find the levels of the factors that which you'll get maximum response or a minimum response. So the type of questions you might consider are these. How is a given response value affected by the set of input variables? If you change, say, factor x1 by a small amount, does the response value change by a small amount, or is it sensitive, and does it change by a large amount? So these kinds of sensitivity questions are of interest. What are the values of the factors for which you will get a maximum response or a minimum response? What's the relationship between the factors and a response close to this maximum or minimum? Again, is it sensitive? But let's begin to look at some of the background, and then in part 3 of this lecture, you'll see 2 examples that we'll walk through. Okay, the equation at the top of the page represents a model in a very general sense, right? This is a two-factor model. Y is the response. We have 2 factors, x1 and x2. Epsilon represents an error term, and this is a 2-factor problem, and the function of these 2 factors is referred to as the response surface. And I tried to allude to this when we were talking about central composite designs in particular. And this also requires that you think about an experiment as a collection of points, or a collection of points in a particular arrangement in a factor space. So the geometric view of experimental design is important to your understanding of response surface methods. So the model is a surface in the space of factors. And we rely on the geometric representation, and we rely on the fact that I can represent this surface graphically as a surface in a in this particular case, in a three-dimensional space. So the two dimensions are the factors x1 and x2, and the third dimension is not a factor, but rather it's the response of the surface. So it's very, if you have a two-factor experiment, it's very easy to represent that in a three-dimensional graphical representation. You'll see throughout this treatment that there are contour plots that we'll talk about, and the contour plots, or sometimes the term level set is used. The contour plot are sets of lines of constant response value, and they're drawn in the plane. And so that contour represents all of the points in the factor plane for which the response value is the same. And then the spacing between contour lines is proportional to the derivatives at that point. And you'll see some examples. Hopefully it'll make it a little bit clearer. Again, the contour represents the response variable. So the spatial arrangement of these contour plots will then help you, because you can infer the derivatives, you can then infer how changing the levels of the factors will result in changes in the response surface. And I apologize for the fact that that bottom line is cut off. But let's look at some of the features of response surface methods. It's direct, it's sequential, it's often iterative, meaning that you will repeat the steps, refining the model at each place, depending on the desired level of accuracy or the goodness of fit. That, as I alluded to on a previous slide, that thinking about experimental design in a geometric sense will help you understand not just central composite designs, but also response surface methods. Right? So that we are clearly here thinking about things geometrically. We have objects in space that represent an experimental design because they're a collection of experimental runs, that the responses at each one of these points forms a surface, and that in these kinds of problems, the questions we're trying to answer are to find typically the maximum or the minimum. So it's very much of an optimization step. And that'll come at the end. You see the 4 steps in this view of response surface methods are first to approximate the model, often by a low-order polynomial. Typically, if you conduct an initial experiment, you might, with a fractional design, compute a first-order model just from the main effects, construct a model, estimate the parameters, and then analyze the complete set of data and fit a more complete model. So approximate, estimate the parameters of the approximate model, analyze the complete set of data that results from the full experiment, and then fit a more accurate model. So it's an approximation to the real relationship, and it typically might be a low-order polynomial, a first-order approximation. Again, think back to fractional factorial designs. Why did we study those? We study those just because so they were very nice tools for approximating a full experiment. You could do that. You could use them to sequentially complete a whole experiment studying it. You can use it initially to measure main effects, maybe two-factor interactions. You can construct approximate models, maybe linear, maybe eventually quadratic models, which you'll use here. So you construct a low-order polynomial. As we saw with central composite designs, we're often working within a bounded region of the independent variables. We might know what the low end is, we might know what the high end is, And if it's a central composite design of one sort, face-centered, box-spankin, that we're adding additional points and forming surfaces. Part 2, estimate the parameters from this low-order model. And here's the key, and that's the text that's in red. The model parameters, that is the coefficients of the factor terms, can be estimated with minimal error, or most effectively if one uses proper experimental design to collect the data. And the form of the experimental design is one of the methods that we've spoken about since the beginning of the semester. It could be, as you saw, box-spankin, which is based on incomplete block design. You might use that as the experimental design to collect the data to then estimate the model parameters. But once you've estimated the model from an initial experimental design, you then have a fitted surface, and then you'll analyze the fitted surface. Is it a good fit? If it's a good fit, you have an accurate model. If it's not a good fit, then we have to find a way to move on and refine our model. In the method that you saw on the previous slide, which I'll show here just once again briefly, the suggestion was that you would repeat this iteratively. You have a model. If it's not a good fit, you might use that as an approximation, then go on and perform another experiment, maybe with a set of experimental runs that are slightly moved in a different area of this dynamic range. But another way of viewing these same steps in response surface methods is to first start with a procedure to move into the optimum region. Now, when I say optimum region of the factor space here, I'm meaning a region in which there's the maximum, or a region in which there's the minimum. Optimum meaning the choice of whichever you're looking for. And you need a procedure to do that. And typically, that procedure is an optimization method. You also need to understand the behavior of the response in this region. So does the value of the response variable vary wildly, or maybe it doesn't vary at all, or it varies very smoothly, but understanding that behavior will allow you to get to that optimum much more efficiently, or perhaps much more quickly. You might think about it that way. Because after all, what we're after is getting to a place where we can estimate these optimum conditions. So you need to understand how things change in that region, and you need to have a procedure for moving about systematically in this region of the factor space. And then we'll need some way of verifying it. But then once you have the model and you know that it's optimum, then it's time for another experiment. Now, I've used the term optimization here quite a bit, and if you are not familiar or you're uncomfortable with it, then by all means please ask. Let's discuss it either on the discussion board, or let's bring it back to class when we meet again on December 2nd. But optimization here we mean is a mathematical procedure to find the maximum of the response variable or the minimum of the response variable, depending on the question we're trying to ask. There are methods in the literature, which is quite extensive, that are either based on local values or global values, or finding a global maximum, or for finding a local maximum. We're interested in a global optimum, a global maximum, global minimum, but we do not want to rely on global values or complete set. We're interested in using procedures that rely on nearby values, local values, for estimating the optimum in order to find optimum operating conditions. But if we're relying on local values, then it means we have to have a way of identifying the region in which we're interested in looking, right? We don't want to start looking in some place far away where there's not an optimum if we don't have a way of getting to the region where there is the optimum. So we have to, we need to have a couple of things in order to do it. We need to know the region, roughly the region we want to get to. We may not know the exact values, but if we're far away, we need to have a systematic way of getting to that region of interest. So typically we have a low order model, a first order, or more often than not a second order model as an approximation to what be something that might be more complex. But here's an example of what one might do or might have. Suppose your design is a fractional factorial design, 1 over p design for k factors, and you might add or eliminate factors, or you might add or eliminate replicates, you might add or eliminate experimental points if it's one of the variations you saw of central composite designs. And the model in this case is shown here. So here's the response variable y, the intercept beta 0, the coefficients beta 1 and beta 2 for the two factors, x1 and x2, and the error term epsilon. We estimate the parameter with the procedure that we know as least squares, and we'll use two methods to get to the optimum. Contour plots are a graphical method, and we might use that as a preliminary strategy to help move in the right direction, to bound the region where we believe the maximum is, and then a numerical procedure that's called the method of steepest ascent. Now, if I'm talking about ascent, of course, that means I'm going upwards, I'm looking for the maximum. There's a method of steepest descent that you would use to get to the minimum. So a graphical procedure, contour plots, and the numerical procedure, that's the method of steepest ascent. What the method of steepest ascent allows us to do is to start with an initial estimate that may be far from the optimum region, which is quite nice because then we can start and have a systematic way of getting to where we want to go, or at least we can get reasonably close if we are starting with a graphical method like contour plots. But let's assume the initial estimate is far from the region of interest. We use the method of steepest ascent to get to the region of interest where the maximum is in as short a time frame, as few steps as possible, get to the general vicinity. And it doesn't have to be a very complicated computational procedure. If we're very far from the optimum, we don't need a very accurate model. Typically, a linear model, first order linear model, is adequate to get us pointed in the right direction. And then later on, we can refine that model. It's sequential, meaning we move step by step, procedure for moving along a defined path towards the maximum in the response. Okay? And we use a very similar procedure, the method of steepest descent. If we're looking for the minimum, what the stepwise procedure doesn't change except for one step where you'll see later on it's the direction in which we're traveling is not in the direction of the maximum, but we change direction to be the direction of the minimum. Now, I've talked about direction, I've talked about steps, and how do you know which direction to go, what direction to travel in. The direction in which we go and the steps are proportional to the regression coefficients beta sub I. So if we have two factors, x1 and x2, and the coefficient of x1 is very large, the coefficient of x2 is very small, then there's the strongest association with x1. And if I'm looking for a place where the response y is very large, or the maximum, it doesn't make sense to look in a direction of x2, does it? Because there's not a strong association between x2 and the response variable y. But yet the coefficients of the model tell me that there's a strong association between x1. And so that's why the coefficients give me a clue as to which direction I want to go. Now, that tells you direction, but the step size is still another factor that you have to determine, but that comes from the setting of the experiment. It comes from knowledge that the experimenter has of the process, of the phenomena that's being studied. It might depend on other practical considerations that you might arbitrarily choose a fixed step size. Or you could, choose it based on the magnitude of the coefficients, or if you generated contour plots, that could help guide you. So there are, it's not just knowledge of the process. There are many other things. It could be somewhat arbitrary. The important thing here is that the direction in which you travel looking for the optimum condition is based on the regression coefficients. Okay, so along this path that you'll traverse, you'll conduct experiments that will help you refine the estimate of the model. You'll continue to conduct experiments until there's no further increase in the response. Then you'll generate a new model and proceed in this new direction, because presumably the additional set of experiments in which you'll generate a new model will give you different estimates of the regression coefficients, and you'll be headed in a maybe slightly different, maybe completely different direction. At some point, you're going to get near the optimum, and how will you know that you're near the optimum? It's probably because your low-order model won't fit anymore. If you're, at the top of a surface that you imagine in your mind's eye that you're looking at a response surface that is like a cone, and the maximum is this point where there's a steep derivative along all points, then you're fitting a first-order surface that won't have a good fit. It'll fit the tangent plane, but it won't fit the response surface. When you know you have a poor fit, then you know you must be close, and then you'll perform additional experiments yet again to get to a more precise estimate. You generate a new model. I apologize for the fact that this picture is slightly out of focus, but I think you can get the idea. This depicts graphically the situation that we've just described. Let's start over here on the right, and you see that these four experiments that I'm circling with the mouse pointer represent an initial fractional experiment. There's, in this case, you see we've added some center runs. Maybe there's other face-centered or axial runs to this, but here's an additional experiment we run, and then we fit a low-order regression model, and from the coefficients beta sub I, so it's beta 1 and beta 2 if it's two-factor, as you see, and determine the direction of steepest ascent. Again, remember that the magnitude of these regression coefficients give us some clue or some idea of the direction in which we can find the maximum. So we follow along the method of steepest ascent, and the step size along here, as you see, is dependent by knowledge of the process or some other practical method that the experimenter might choose. Eventually you're going to get to a point where you don't have a good fit, and then you see I'm circling another set of experiments, another fractional run with center points. It'll give us a new direction, and I'll follow in this direction that's going toward the right-hand side of the screen. And the step size, as you can see, is different. There's larger steps here than there are over here. Might be chosen for process knowledge or some other reason. Finally, I get to a point where there's a lack of linear fit. I might be at the top of that cone, and I'm going to run an additional set of experiments, another fractional run. And now I might try to fit a different surface. So rather than a linear surface, we'll try to fit a higher order surface. And I'll proceed on with that second phase. So this is the method of steepest ascent. And steepest descent is a similar procedure. It's just that the direction you're traveling is not towards the maximum, but towards the minimum. And you could see that in this example. So, for example, the regression model at the top of the page shows one where I have two factors, T may be temperature, P may be pressure, and the regression coefficients are minus 0.295 and 0.33. And the regression coefficients represent the derivatives, or the rate of change in the response variable with respect to the factors along each of those axes. Now, in this case, neither one stands out as being more significant than the other. So the direction in which I'll travel is depicted by the vector D for direction. Here is the direction, or related to the direction, in the direction of temperature and in the direction of maximum pressure. If this is the signs are set for the direction for steepest ascent. If it's steepest descent, there would be the opposite sign. Now, because I'm in factor space, which is normalized, and these coefficients are actually in terms of the dimensional quantities, I have to normalize them. So although not typeset correctly, this is the magnitude, the square root of the sum of the squares. The plus sign is missing. This should be extended. But 0.44 is the magnitude of this directional vector. And the direction in which I actually travel in the factor space is given by this scaled directional vector u. Right? So it's the directional vector based on unit quantity. Okay. So if this is an initial model and I have a two-factor design, this is with skipping the steps in between. This is the model that actually gives me an optimal response where there's a very significant influence of temperature T and much less influence of pressure P. Okay, so by following this procedure of steepest ascent, starting with this initial model, going in this direction, I eventually wind up with this model for the two factors, temperature and pressure. Now that works well, and is a procedure that we recommend you follow for linear models. If you have a second order model, so here's one where I don't just have contributions from the two factors in a linear combination, but I have also second order contributions by factor x1 and x2, and I also have an interaction effect of x1 and x2. Then the design you would choose would be based on central composite designs, right? Remember, we add the additional points of central composite design, the axial runs and the center runs, so you could fit a second order model such as the one that's seen here. So that's the experimental design you'd use. Here's your model. The estimation of the parameters beta 0 and beta 1 through those seen here is still by least squares. And the optimization, instead of just being contour plots and method of steepest ascent, is slightly different. One still uses contour plots as the graphical component to give you an idea of the direction in which you want to choose, but you'll also use canonical analysis rather than the optimization procedure in order to find the maximum. By canonical analysis, you'll see what we mean as eigenvalue, eigenvector analysis. But the design here, again, for a second order response surface strategy is central composite design. You'll see here is the factorial design, and what may be a fractional design. You add the star center point plus additional points and form this central composite design. So, this is the same kind of diagram we showed that I called the face-centered design. Although this picture isn't the greatest, these are axial runs that are not necessarily on the face. So this one is off the face here, this one is off the front face, this is off the back face, and as you can see better here from the top face and the bottom face respectively, that these are axial rather than face-centered runs. So this is a traditional or classical central composite design. So you want to find the optimum, again, for this set of operating conditions for the factors, and characterize the nature of the response surface, and that's again done by estimating the coefficients, and that'll lead you to either the maximum or the minimum. So again, you start with the central composite design, estimate the coefficients of the model, the second order surface as you saw. That gives you the characterization, which might be either, you see graphically through the contour plots and or through the eigenvalue, eigenvector analysis, and that will lead you to the maximum or minimum. Now, because it's second order, that you may also have saddle points, right? So the optimal operating condition might be the maximum of one factor, but the minimum of the second, if I have two factors as shown in the previous. So you have to allow for more, and that's why the method of steepest ascent or descent by themselves isn't sufficient or can't work in these conditions where I'm trying to fit a second order surface. You must allow or must have a procedure for finding either a maximum, minimum, or the combination of the two, that is where you have a saddle point. You might have a ridge where there's a maximum of one and there's no change in the second. But we talked about contour plots a lot. Let's look at a couple of examples. I advocate using this as a procedure for inferring something about the properties in the same way that we've used box and whisker plots or scatter plots in classical experimental design. So they're graphical analysis of a fitted model. You can see something about the range of the response values by looking at a set of contours. And here's an example. There are two factors, x1 and x2. As you can see, if I bring the mouse down, this is the x1 axis. You see that it's scaled again, dimensionless, between -1 and 1. X2 between -1 and 1. And the third axis here is the response variable. In this case, again, yield, y. But by contour plots, we mean these lines that you see in the x1, x2 plane. And this is colored, and the red area is closer or hotter, it's closer to the maximum. The blue is colder or further away from the maximum. And these lines or contours in the factor plane represent contours of constant response value. So that every point along this line has the same response variable, value of the response variable. Similarly, this contour and the yellow contour, all points along this contour, have the same value of the response variable all the way back to this corner. The spacing between them is indicative of the slope of the surface. So if you follow this back corner where x1 and x2 are both 1 and 1, and you follow the mouse pointer, if you can, a little bit, you see the spacing of the contour plots are closer together. But as I get closer to the red lines, the maximum, you see that it gets further apart. So the slope is decreasing. And you can see that by looking at this 3D model, right? So this corner back here is so far away that you don't even see it in the 3D plot. Right? But as you travel up the surface and as you travel this way, the slope first increases very rapidly and then increases less rapidly. So here's a 3D plot of a fitted surface from a second order model, and these lines represent what's referred to as the contour plot. Here's one that's not in color. So in picture A, which is up on the top on the left, shows a maximum response. The value of the response to the outer is 60, the second 70, and the innermost is 80. So you know by looking at this set of contour plots, if I travel in a direction toward the center, I'm traveling toward the maximum. This is minimum response. So I go 60, 50, 40, and traveling in the same direction would lead me toward the minimum. This set of contour plots on the bottom represents a saddle point. Right? If I'm traveling along this axis, I'm going 70, 85, 70, 65, 60. Here's 60, 65, 70. So in your mind's eye, if I'm traveling from the top, my values are going down and then going back up. So this is a minimum in this direction. If I'm traveling along this perpendicular axis, I'm going from 50 to 55, it's going to a maximum, and then 55 to 50. So in one direction I have a minimum, the other direction a maximum. Hence, there's a saddle point right around here in the factor space. Right. Maximum, minimum, saddle point. So not much more needs to be said about contour plots. You can generate those in R and in any other package that you might use. The second tool that you'll use if you have second order models that you're trying to fit is what's referred to as canonical analysis, or really a normal form. Now, eigenvalues, eigenvector analysis is something that's easy to do, but maybe sometimes hard to understand or sometimes hard to appreciate. And you might wonder why does it appear in this context, right? Because by eigen or principal values, what we're really referring to is what I think of as a canonical or a normal form. Normal form meaning a standardized form or a standardized representation. That's the only way that I can relate things that are problems maybe in manufacturing or physics or sociology or finance or cell behavior, or as you'll see in one of our examples in the next section, paper helicopters. A standardized or normal form, an approach to analyzing problems in this standardized way allows you to have a method for which you can regularly get to a solution. So there are two things we have to realize. First of all, that when I have factors in their standard